Okay, in this screencast, we'll begin another series on simple Haar wavelets. Our treatment will be based on the great textbook Wavelets Made Easy by Ives Nivergelt. So let's consider three graphs. The horizontal axis will be called R, and then the vertical axis will be called S, right? So, and that's we're modeling signals, and let's assume that we're doing our signal modeling with a function. So there's this function, some sort of function. Let's make it negative, although we're not interested in negative values in this case. And the function is modeled on the real interval from 0 to 1. Or rather, the function models the signal, right? Okay. So since oftentimes it's very expensive to represent the entire function, it's actually downright impossible, because at some point we have to go discrete, be finite. So we have to approximate the function with sample values. So these green circles are sample points. They were just sampling our signal at specific points. Okay, and then let's draw these sample points. So approximately, they're supposed to be the same green points as on the graph on the left. Okay, so let's see, we have these simple sample points rather. Okay, 1, 2, 3, 4, 5, 6, and 7. Right, so these sample points. Okay, the last one was supposed to be a little bit to the left of 1. All right, and then once we have the sample points, we can model the function, or approximate the function, with the so-called step function, right, where each interval, or each sample point rather, from the original function is represented by an interval, right, or a stair step that starts from the sample point and ends at the next sample point horizontally, like is drawn horizontally, goes horizontally, ends at the next sample point, but does not include the next sample point, right? So this is our original function. Let's call it f of r, and it could be, let's say, speech signal, or some sort of image signal, right? Light signal, right, or grayscale signal. So this is our sampling sample of that signal, and this is the step function, right? And the step function is supposed to approximate, right, is designed to approximate the original f of r equals s function, or the signal represented by that function, rather. That would be more precise. And it is denoted by f tilde. Okay, so let's talk about intervals and unit step functions. So we need to make precise the notion of a step, right? And the step is represented by an interval from u to w, and I am using Nivergelt's notation. So this means the set of all points beginning at u and including u and excluding w. So it's r such that r is greater than or equal to u, but strictly less than w. So I guess another way to look at it, this is a half-open interval. Alright, so this would be probably would be a more common notation, but I'm going to stick with notation from the text. Wavelets made easy. Okay. All right. So then there is this unit step function, right, that allows us to represent each step in the step function, right, in terms of the sum of the unit step functions. And the unit step function, right, from 0, including, right, 0 to 1, excluding 1, psi of 0, 1 of r is equal to 1 if r is greater than or equal to 0 but less than 1, strictly less than 1, and it is 0, uniformly 0 everywhere else. So in terms of the graph, let's draw a simple graph, what that step function is. So if we this is our r-axis and this is our s-axis. All right. So the function is gonna go like this. So it's like step, a stair step from 0 to 1, right, excluding 1, and then beginning at 1, right, and to the left of 0 it's gonna be 0, right, everywhere else. So all right, let's manipulate. Let's suppose that for some purpose, well, it is often useful to go from 0 to some value w, right? So that unit step function is defined as psi of well, phi rather. This is not psi, I said psi earlier, so this is a different letter, so this is phi of r from 0 including 0 to 1, and excluding to w rather, and excluding w is going to be equal to 1 if r is less than or equal to 0, is greater than or equal to 0 but less than w, and 0 otherwise. Right, so let's graphically draw this. This is going to look like we're going to go from 0 to w, right, and excluding w. So this is, we're going to have 1, and then from w included, and then to the left of 0, 0, we're gonna have also 0. Okay, so if we wanna start our interval from some value u and included, and go to some value w excluded, right? So phi of r on that interval is gonna be equal to 1 if the value of r is greater than or equal to u and strictly less than w. And 0 everywhere else. Okay, so we can draw this graphically. This is u, this is w. So we're at 1 from u included and to w excluded, right, and then 0 everywhere else. Okay, and finally we can scale the unit step function. So by multiplying it by some scalar c, let's say c times phi from u included to w excluded of r is equal to C, right? It's equal to C if C, yes, it's C, if R is greater than or equal to U and less than W, and 0 everywhere else. So graphically this will look like this. So this is U, this is W, and this is C. So we're at 1 here, right? Okay, it's supposed to be just a thick line, and then 0 everywhere else. We're at C there, and then 0 everywhere else. Okay, so let's say that we have the value of the original function, right, that represents some signal that we're trying to model, luminosity or sound. F of rj equals sj, so that's a sample point, s sub j. So here is s r sub j, right, time, for example, and that time r sub j, we have the sample point s sub j, right? So then to that sample point in our step function, right, there corresponds the following value: s sub j equals phi of r sub j included to r sub j plus 1 excluded. Okay, so this is the value s sub j times that stair step value. Okay, so we're scaling it to be on that. And now we have the unit step function, which is phi, right? And we can represent our step function, right, as the sum of our sample values and unit step functions. So the first sample value was the 0th, rather, s sub 0 times phi on the first interval from 0 to r1, whatever that value of r1 is. So we don't really care so long as we have 2 to the n number of intervals. Right, so it's a power. The power of intervals is the power of 2. The number of intervals is a power of 2. Okay, so then the first value is the second value is sub 1, right? Or the first value, if we are beginning to count from 0, times our second unit step function, and all the way plus to value n minus sample value n minus 1 times our unit step function on the interval from r sub n minus 1 included to r sub n excluded. So this can be represented as a sum from j equals 0 to n minus 1 s sub j times the value of the unit step function on the corresponding interval from r sub j to included to r sub j plus 1 excluded. So this is how we represent the step function that in turn represents the original signal function, f of r equals s. So this is on the horizontal axis we have these intervals, so 0 from 0 to r minus 1, from r minus 1 to from r1, from r1 to r2, and then from r n minus 1 to rn. Alright, so okay, so this is our intervals. Alright, so let's consider some examples. Let's suppose that we have two sample values, S0 and S1. S0 is the sample value at R sub 0, and then this tuple is equal to 0, 5. So at 0, the value of the signal function is 5. And at R sub 1, the value is S sub 1, and that value is equal to, just for the sake of example, right, so R1 is half and S1 is 2. Okay, so we can draw this table. So this is the value of J. There are two possible values of J, 0 and 1. And R sub 0 is 0, and R sub 1 is half. So at R sub 0, the value of the signal is 5, and at R sub 1, the value is 2. So the step function f tilde is the sum from J equals 0 to 1. So these are the possible values of J, because we have two sample points. And right, so at each value of J, we compute this product, S sub J times phi, the unit step function on the interval from R sub J included to R sub J plus 1 excluded. And this is if we write it out. I'm going to have 5 times phi on the interval from 0 included to 1 over 2 excluded, plus two times phi on the interval from 1 over 2 included to 1 excluded. And let's draw this graphically. Okay, so from 0 to 1 over 2, excluding 1 over 2, we are at 5, and then from 1 over 2 to 1, we are at 2. Okay, so here's another example. Right, so in this case we have 8 samples. Right, the first sample point is taken at 0, the second sample point is at 1 over 8. Then we have another sample point at 2 over 8, then at 3 over 8, well 2 over 8, 1 over 4. Okay, and then 4 over 8 is half, right? And then 5 over 8 and 6 over 8. And 7 over 8, right? And then from 7 over 8 we go to 1. So this is, yeah, it's a power of 2, 2 to the third. So this is our first, second interval, third interval, fourth interval, fifth interval, sixth interval, seventh interval, eighth interval. Okay, so the step function can be represented as the sum. Okay, a sum of those stair steps. 8 times phi on the interval from 0 excluded to 1 over 8. 0 included rather to 1 over 8 excluded, plus 6 times phi on the interval from 1 over 8 included to 2 over 8 excluded, or 1/4, right, excluded. Okay, plus 7 times phi on the interval from 1/4 included to 3 over 8 excluded. Then 3 times another stair step represented by phi from 3 over 8 included to 1 over 2 excluded, plus 1. Okay, so 1, 2, 3, 4. Okay, right, so we're at 1 now. 1 times phi from half included to 5 over 8 excluded, and then plus another 1 times phi from 5 over 8 included to 3 over 4 excluded, 5 over 8 included to 3 over 4 excluded, and finally 2 times phi from 3 over 8 this time included to 7 over 8 excluded, and plus 4 times phi from 7 over 8 included to 1 excluded. Okay, so and then graphically this can be represented as, let's do this. So the highest value, sample value, is 8. So on the first interval we go at 8, on the second at 6, then third 7, then the next at 3, then we're at 1. Right, here's 1, then there's another one. Okay, another one, then we're at 2, and then finally on the last one we're at 4. Right, this is stair steps. So these are the beginning of every stair step that's included in that step, and the end is not included. So okay, so this is 6, 8, and 6, and then this is here we're at 7, and here we are at 3, and 1, 1. And so this is our representation in terms of the step function of the original signal. Okay, well, thank you. This is to be continued.